All right, so this lecture is on change of basis. So I had posted some notes on Blackboard, and the homework is the set of problems at the end of the section. So let me go over a little bit again, the change of basis matrix, and then I'll work on some of the homework problems. So let's see. We start with the vector space V, where the dimension of the vector space is n. And suppose we have an ordered basis, script f, which is a sequence of n vectors. And if you take any vector v in the vector space, capital V, you can write V as some unique linear combination of these basis vectors. And what is called the coordinate vector of V with respect to the basis script f. So I write V in square brackets with an F around it. And that's just these vectors, these coordinates, these scalars, x1, x2, up to x sub n. So this does not mean the vector in Rn with these coordinates. These are the coordinates of the vector V with respect to a given basis. And suppose we have a second basis, G1 up to Gn, another ordered basis for V. So we can write the vector V again as a unique linear combination of the vectors in this basis. And with respect to this basis, we have a coordinate vector, y1, y2 up to yn. So these are coordinate vectors for the same vector, but they're different numbers because these are the coordinates with respect to a different basis. And we're going to prove, and in fact construct, an n by n matrix P such that if I take the coordinates of V with respect to F and I multiply it by the matrix P, I get the coordinates for the vector V with respect to G. And this is called the change of basis matrix. And the construction is described in the notes in Theorem 1. So again, we have dimension of V, the vector space is n, and we have bases F, F1 up to Fn, and G, G1 up to Gn. So every vector in V can be expressed with respect to the basis F and can also be expressed with respect to the basis G. So for all J from 1 up to n, we can write the vector G sub j as some linear combination Pij f sub I goes from 1 up to n. And I claim, first of all, the matrix P, whose coordinates are the Pij's, is invertible. And why is that? So notice that in the matrix Pij, the jth column of P is P1j, P2j, down to Pnj. That's exactly the coordinates of the vector Gj with respect to the basis F. And since these are both bases, we can also write each vector Fj as a linear combination of the vectors in G. So we can write each vector Fj as summation Qij G sub I. This is a Q and this is a G. I goes from 1 up to n. So Q11 down to Q1j down to Qnj. This is the coordinate vectors of the coordinate vector for Fj with respect to the basis G. And again, we have a matrix Q with these numbers as the coordinates. So I have two bases for my vector space. I can write each Gj as a linear combination of the Fs. I can write each Fj as a linear combination of the Gs. This gives me the matrix P. This gives me the matrix Q. And let's multiply P times Q and Q times P. So let me just recall. So I have the vector Gj is summation Pij F sub I. I goes from 1 up to n. The vector F sub j is summation Qij G sub j. I goes from 1 up to n. P is the matrix of Pij's. Q is the matrix of Qij's. So these are n by n matrices. What is the ijth coordinate of the matrix PQ? This is summation Pik Q Kj. K goes from 1 up to n. How can we understand this? So I have G sub j is summation I goes from 1 to n Pij F sub I. Each vector Fi is a linear combination of the G's. So let me just change my letters. Suppose I write F sub I well, let me call this K. So G sub j, instead of using the index I, I'm going to use the index K, Pkj F sub K. What is F sub K? If I just replace J by K, I get summation I goes from 1 up to n, Q Kj, oops, sorry, F sub K, I'm replacing J with K, and this should be an I, of course. So F sub K, if I let J equal K, I have summation I goes from 1 to n, Q sub Ik Q sub I k G sub I. If I interchange my summations, I goes from 1 up to n, k goes from 1 up to n. I have qik pkj times the vector g sub I. So gj is this linear combination of the vectors g sub I, but the gj's form a basis. This has to be 0 if I is different from k, and 1 this has to be 0 if I is different from j, and 1 if I equals j. So summation, k goes from 1 up to n, qik pkj, this is 1 if I equals j, and 0 if I is different from j, which is exactly what we denote as delta ij. This is just the number which is 0 or 1, depending on whether I equals j or not. This is what is called the Kronecker delta. That's just the name of this very traditional function in mathematics. But another way of saying this is, well, it's exactly this. The ijth coordinate of PQ is this, is delta ij, which means PQ is the identity matrix, right? So this is a fundamental calculation which you need to go over at home again and again to make sure, oops, yeah, you understand it, sorry. This says that QP is equal to the identity. And if we want to show that PQ is equal to the identity, we do the same kind of calculation starting with FJ. So the vector Fj is summation I goes from 1 up to n, Q sub I j, G sub j. Or if I want to use a different letter index of summation, summation k goes from 1 to n, Q sub kj, G sub k. But each G sub k is summation P I k F sub I. I goes from 1 up to n. This is how we express every vector in the basis G as a linear combination of the vectors in the basis F, and I can plug that in here. So this is summation k goes from 1 up to n, qkj, summation I goes from 1 up to n, pik f sub I. I can interchange summations. I get pik qkj times f sub I equals fj. So this also has to be the Kronecker delta. Summation pik qkj, k goes from 1 up to n, is the Kronecker delta, which means PQ is also the identity matrix. So I prove that PQ is the identity and QP is the identity, which means Q is the inverse of P. Right? Because you multiply them in either order, and you get the identity. And I claim that P and Q are change of basis matrices. That if I take the vector V and I look at its coordinates vector with respect to G, if I multiply by the matrix P, I get the coordinates of V with respect to F. And if I take the coordinate vector of V with respect to F and multiply by Q, I get the coordinate vector for V with respect to G. So this is theorem 2 on page 5. And let me prove this. So we have G sub k if summation I goes from 1 up to n, P sub I, K, F sub I, and P is the matrix Pij, or G sub j. Right? So suppose that the coordinates of V with respect to G are y1 to y sub n. This means the vector V is this linear combination of y sub j, G sub j. J goes from 1 up to n. But G sub j can be written like this. So let me make this one long line if I have to. V is summation yj, G sub j. J goes from 1 up to n. But Gj is summation I goes from 1 up to n, Pij, F sub I. So when I expand all this, I get some linear combination of the Fi's. So this is summation I goes from 1 up to n. Summation j goes from 1 up to n. I have Pij, y sub j. So the coordinate vector for V with respect to F is summation j goes from 1 up to n, P1j, yj, summation j goes from 1 up to n, P2j, yj, down to summation j goes from 1 up to n, Pnj, yj. That's exactly the matrix P applied to the vector y1, y2, down to y sub n. When you multiply row into column, this is what you get. So this is P, and this is the coordinate vector for V with respect to G. So I've just proved exactly what I wanted to prove. If I take the coordinate vector of V with respect to G, multiply it by the matrix P, I get the coordinate vector for V with respect to F. And by exactly the same type of calculation, if I take the coordinate vector for V with respect to F, multiply it by the matrix Q, I get the coordinate vector for V with respect to G. Okay, so that's the theory that leads up to the homework problems. And now I'll start the homework problems, okay? Any questions before I start that? So these are the exercises on page 7 of these notes. So in problem number 1, we have the vector space V is R2, and we take F to be the set of vectors 1, 3, and 2, 7, and G to be the set of vectors 2, 0, and 1, 1. So we want to prove, first of all, F and G are bases for R2. So each a basis is a set of 2 independent vectors. So we have to show that these vectors are linearly independent and these vectors are linearly independent. Let's start with G because that's easier. So suppose y1 times 2, 0 plus y2 times 1, 1 is equal to the 0 vector. But this vector is 2y1, 0, and this vector is y2, y2. And when you add them, you get 2y1 plus y2, y2. And that's equal to the 0 vector if and only if y2 is 0 and 2y1 plus y2 is 0. But since y2 is 0, this means 2y1 is 0, which means y1 is 0. So the only linear combination of these two vectors, which gives the 0 vector, is the 0 combination. So these two vectors are linearly independent. So this is a basis. What about for F? Suppose I take x1 times 1, 3 and x2 times 2, 7. This is x1 plus 2x2, 3x1 plus 7x2. Does that equal the 0 vector? Well, when? We have to have x1 plus 2x2 equals 0, and 3x1 plus 7x2 equals 0. What are the solutions? 2 equations and 2 unknowns. Let's see, this says that x1 is minus 2x2. So 3x1 is 3 times minus 2x2 plus 7x2. Has to equal 0, but 7 minus 6 is 1. So x2 is 0, which means x1 is 0. So these are both bases for R2. Okay. Any questions about that? It's just proving 2 vectors are linearly independent. What about the change of basis matrices? So I want to write G1 as some linear combination of the vectors in the basis. So I'm writing the vectors in the basis G as linear combinations of the vectors in the basis F. I have to find these coefficients. Let's see, what does that mean? What is G1? So let me just write this down again. F, I have the vector 1, 3. I'll call that F1. And F2 is the vector 2, 7. G, I have the vector 2, 0. I'll call that G1. And the vector G2, which is 1, 1. So the vector P, the matrix P, comes from writing the G's as a linear combination of the F's. The matrix Q, comes from writing each F as a linear combination of the vectors in G. So F is going to be Q1, 1 times G1 plus Q21, G2. F2 will be Q12, G1 plus Q22, G2. The vector G looks easier than the basis G looks easier than the basis F. So let me calculate these numbers Q first. This is Q11 times the vector 20 plus Q21 times the vector 11. This is the vector 2Q11 plus Q21, Q21, and that's supposed to equal F1, which is the vector 1, 3. Let me just solve this. This is easy, right? This is 2Q1 plus Q21 equals 1, but Q21 equals 3. So this says that 2Q11 plus 3 is 1. So 2Q11 is minus 2. So Q11 is minus 1. So in the matrix Q, the first column, Q11, Q21, is minus 1, 3. And to find the second column, F2, this is Q12 times 20 plus Q22 times 11. Again, this is 2Q11 plus 2Q12 plus Q22 equals F2, which is the vector 2, 7. So this says that Q22 is 7. That's there. 2Q12 plus 7 is equal to 2. So 2Q12 is minus 5, or Q12 is minus 5/2. So if I did my calculation correctly, this is the matrix Q. And this matrix has the property that for any vector V, if I write V with respect to the basis F, Q times that gives me the vector V with respect to the basis G. Let's see. Now, there's a lot of arithmetic here, and maybe I made some mistakes. So I always make mistakes, so I always like to check. The vector F1 is the vector 1, 3. If you write that with respect to the basis F, the coordinate vector is 1, 0. So Q applied to the coordinate vector F1 with respect to F, that's Q times the vector 1, 0. That's minus 1, minus 5/2, 3, 7. If I apply that to 1, 0, I get minus 1, 3. That's supposed to be the coordinate vector of F1 with respect to G. So let's just check. This means minus G1 plus 3 G2. Minus G1 is minus 2, 0 plus 3 times 1, 1. That's 3 minus 2, 3. And this really is F1. F1 was the vector 1, 3. So looks like this is correct. So that's computing the change of basis matrix Q. Okay, well, let me start from the beginning and compute the change of basis matrix P. So again, we have F is 1, 3, 2, 7. The basis G is 2, 0, 1, 1. To find the matrix P, I have to write each vector in G as a linear combination of the vectors in F. That is, I want to write 2, 0 as some linear combination P11 times the vector 1, 3 plus P21 times the vector 2, 7. And I want to write the vector 1, 1 as some linear combination P12 times 1, 3 plus P22 times 2, 7. And these will give me the coordinates of the P matrix. So I just have to solve systems of linear equations. Let's see, this is P11 plus 2P21. This is 3P11 plus 7P21. So I'm solving the equations P11 plus 2P21 equals 2, 3P11 plus 7P21 equals 0. So I could just take the first equation, multiply it by 3. I would get 3P11 plus 6P21 equals 6. I subtract, I get P21 is minus 6. And then P11 is 2 minus 2P21 is 2 minus 2 times minus 6 is 14. So in the matrix P, the first column will be 14 minus 6. Now I want to write 1, 1 as a linear combination of these two vectors. What is this? This is P12 plus 2P22, 3P12 plus 7P22. That vector has to equal 1, 1. So we're solving the equations P12 plus 2P22 equals 1. 3P12 plus 7P22 equals 1. Again, I'll take this equation, multiply it by 3, 3P12 plus 6P22 equals 3. When I subtract, I get P22. 1 minus 3 is minus 2. And then P12 is 1 minus 2P22. 1 minus 2 times minus 2, that's 5. So P12 is 5. P22 is minus 2. So it looks like this is my matrix P. So what I just calculated is the matrix P is 14 minus 6, 5 minus 2. The matrix Q that I calculated was minus 1, 3, minus 5 halves, 7. Now, they're supposed to be inverses of each other. So let's compute P times Q. 14 minus 6, 5 minus 2, minus 1, 3, minus 5 halves, 7. I get minus 14 plus 15, 6 minus 6. Here I have 14 times minus 5 halves. That's minus 35 plus 35. And minus 6 times minus a half is 15 minus 14. Lo and behold, I do get the identity. And if I calculate QP, I'll also get the identity. So that's a good sign. Okay. Now, in part C, I want to compute the coordinate vectors VF and VG for the vector V equal to 5, 3. So I computed change of basis matrices. When I know the coordinates of V with respect to F or G, I can get the coordinates then with respect to G or F. So maybe I'll start by finding the coordinates of V with respect to G, right? Because G is an easier. So I want to find this as Y1 times G1 plus Y2 times G2. G1 is the vector 2, 0. G2 is the vector 1, 1. So this is 2y1 plus y2, y2. And that's supposed to equal the vector 5, 3. Which means y2 is equal to 3. And 2y1 plus y2 is 5. Y2 is 3. So y2 is, you see, y1 is 6 minus y2 is minus 1. Sorry, y sub 1 is minus 1. So the coordinate vector for V with respect to G is minus 1, 3. That's interesting. So if I take the vector 5, 3, this has to equal 5, 3. So y2 is 3. Y2 is 3. Oh, sorry. Y2 is 3. So 2y1 plus y2 is 2y2 plus 3 equals 5. So y2 has to equal 1. So this is 1, 3. And how do we get the coordinates of V with respect to F? That's P times the coordinate vector of V with respect to G. The matrix P is 14 minus 6, 5 minus 2. And the coordinate vector of V with respect to G is 1, 3. So I get 14 plus 15 is 29, minus 6 plus 6 sorry, minus 6 is minus 12. So I never expect to get these things right the first time, but let's check. This is supposed to be the coordinate vector of V with respect to the matrix F. So 29F1 minus 12F2 is 29 times the vector F1, that's the vector 1, 3, minus 12 times the vector F2, which is 2, 7. So this is 29, 3 times 29 is 87, minus 24 times 84. 29 minus 24 is 5. 87 minus 84 is 3. That's exactly what it's supposed to be because F was 5, 3. So somehow, miraculously, all the arithmetic works out, and this is correct. Part D is just a restatement of the theorem, so I shouldn't even have put that in. I'm going to take that out. Okay. That's what it is. Can't argue with success. Okay. Let's go to number 4. So in the number in 4, we have the vector space R3, and we have 2 sets of vectors. F consists of the 3 vectors (0, 1, 1), 1, 0, 1, and 1, 1, 0. And G consists of the vectors 1, 0, 0, 1, 1, 0, and 1, 1, 1. So I'll call this F1, F2, and F3, and G1, G2, and G3. So first step is to prove these are bases. So let's prove F is a basis. So if I have a linear combination of these vectors, x1, f1, plus x2, f2, plus x3, f3 equal to the 0 vector, what does that mean? It means the 0 vector is going to be x1 times 0, 1, 1 plus x2 times 1, 0, 1 plus x3 times 1, 1, 0, which is the vector x2 plus x3, x1 plus x3, x1 plus x2, which means we have the following system of 3 equations and 3 unknowns to solve. x2 plus x3 equals 0, x1 plus x3 equals 0, x1 plus x2 equals 0. So this equation says, for example, that x3 is equal to minus x2. So the second equation becomes x1 minus x2 equals 0. The third equation was x1 plus x2 equals 0. If we add, we get 2x1 equals 0. So x1 is 0. And if x1 is 0, x1 plus x3 is equal to 0. And x2 is minus x3 equals 0. So x1, x2, x3 are all 0. So F is a basis. They're linearly independent. Right? Any questions about that? To prove G is a basis, if the 0 vector is some linear combination of 1, 0, 0 plus 1, 1, 0 plus 1, 1, 1, if we add up these vectors, we get y1 plus y2 plus y3, y2 plus y3, and y3. If this is equal to 0, the 0 vector, y3 equals 0. Then y2 plus y3 is 0, so y2 is 0. And if y2 and y3 are 0, y1 is 0. So I've just proved that both of these sequences of vectors are bases for F3. And I want to find the change of basis matrix to convert from coordinates in F to coordinates in G, and from coordinates in G to coordinates in F. So how do I do that? It's just a bit of a calculation, but in math, you have to do calculations sometimes. So what are the Pij's and the Qij's? I want to write each G sub j as some linear combination. I goes from 1 to 3 of Pij F sub I. So what does that mean? So G1 is 1, 0, 0. And I want to write that as some linear combination P11 F1 plus P21 F2 plus P31 F3. Let's see, what is this vector? This is P21 plus P31, P11 plus P31, P11 plus P21. So I have to solve the equations. P21 plus P31 equals 1. right? This is going to be 1, 0, 0. P11 plus P31 equals 1. And P11 plus P21, sorry, equals 0, equals 0. So this says that P31 is minus P11. And this says P21 is minus P11. So P21 plus P31 is minus P11 minus P11, or minus 2P11 is equal to 1. So P11 is minus a half. P21 is plus a half. And P31 is also plus a half. So that gives me, I've solved this equation for j equals 1. What about G2? I mean, there's no alternative to doing the work. That is, sometimes you just have to do the work. There's a lot of work. But this is how you learn what's going on, by doing the calculations and checking them. So G2, what is the vector G2? G2 is the vector 1, 1, 0. Is going to be a linear combination of the 3 vectors in F. So that's going to be P12, 0, 1, 1 plus P22, 1, 0, 1 plus P32, 1, 1, 0. So that's the vector P22 plus P32, P12 plus P32, P12 plus P22. So we have to solve 3 equations and 3 unknowns. P12 plus P22 equals 0. Sorry, well, that's true, but I should put them in order. P22 plus P32 equals 1, and P12 plus P22 equals 1. Oops, let's see. P22 plus P32 equals 1. P12 plus P32 equals 1. And P12 plus P22. All right, let me write this down correctly. So this is P22 plus P32, P12 plus P32, P12 plus P22, and this is supposed to be the vector 1, 1, 0. So this equals 1, this equals 1, and this equals 0. So if I solve these equations, I'm doing it by hand. So P22 plus P32 equals 1. P12 plus P32 equals 1. P12 plus P22 equals 0. If I subtract this third equation from the second, I get minus P22 plus P32 equals 1. The first equation was P22 plus P32 equals 1. If I add, I get 2 P32 equals 2. So P32 is equal to 1. If P32 is 1, P12 is 0. If P12 is 0, P22 is 0, and P32 is equal to 1. So this looks like the second column of the P matrix, which I could have done just by looking, because 0, 0, 1 is exactly what works. Okay, and then I need to get the third column of the P matrix. I've written G1 and G2. Now I have to write G3 as a linear combination of my vectors. So G3, which is the vector right. These are my bases. G3 is the vector 1, 1, 1. And I want to write that as a linear combination of the F's. So that's P13 F1 plus P23 F2 plus P33 F3. These are the F's. So when I put this together, what I get is P23 plus P33, P13 plus P33, P13 plus P23. And this has to equal 1, 1, 1. And I can actually do that by looking, because if each of these is equal to a half plus a half is 1. So my matrix P, I just found the third column is a half, a half, a half. And for the first column, I got minus a half, a half, a half. And for the second column, I got 0, 0, 1. Huh. All right. There's probably a pretty good chance this is right. You never know. So this matrix P has the property that if I take a matrix V, write the coordinate vector with respect to G, multiply it by the matrix P, I should get the coordinate vector for V with respect to F. So let's try that, as we have to do in this problem in part C, for V to be the vector 3, 8, 1. So I want to write this as a linear combination of the vectors in G. So sum y1 G1 plus y2 G2 plus y3 G3. That's y1 times 1, 0, 0, y2 times 1, 1, 0, y3 times 1, 1, 1. This is the vector y1 plus y2 plus y3, y2 plus y3, y3. And that's supposed to equal 3, 8, 1. So the coordinate vector for V with respect to G, that's y1, y2, y3. This says y3 is equal to 1. This says 1 plus y2 is 8, so y2 is 7. This says 1 plus 7, which is 8, plus y1 is 3, so y1 should equal minus 5. So if I did this right, hopefully I did, This is the coordinate vector for V with respect to G. So what is PVG? That's the matrix minus a half, a half, a half, 0, 0, 1, a half, a half, a half, times the vector minus 5, 7, 1. Let's see, let me do this calculation. This is 5 halves plus a half is 6 halves is 3. This is minus 5 halves plus a half is minus 4 halves is minus 2. This is minus 5 halves plus 7 plus a half. Minus 5 halves plus a half is minus 2 plus 7 is 9. So if we're lucky, the coordinate vector for V with respect to F is this. So let's check. 3F1 minus 2F2 plus 9F3. That's 3 times the vector 0, 1, 1 minus 2 times the vector 1, 0, 1 plus 9 times the vector 1, 1, 0. This is minus 2 plus 9, that's 7. This is 3 plus 9 is 12. This is 3 minus 2 is 1. Let's double check. Minus 5, 7, 1. So this is 5 halves plus a half is 3. Minus 5 halves plus a half is minus 2. Minus 5 halves plus a half is minus 2 plus 7 is 5. This should be a 5. Let's see if that's better. So I get minus 2 plus 5 is 3. 3 plus 5 is 8. 3 minus 2 is 1. 3, 8, 1. And that's exactly what I started with. So a miracle has happened, and this looks like it's correct. So fortunately, this is all being recorded, so you can look it over on the YouTube channel if you like, and that's what we have. So these are not the world's easiest problems, but you know, up to a 300 level math class, you don't expect the world's easiest problems anymore. You're way beyond calculus here. Right? Any questions about this? I mean, I don't know. I hope this is helpful, but this is a basic basic in calculus. So again, we have a vector space of dimension n. We have a basis F, a basis G, and we have matrices P and Q, where if you take the coordinate vectors, the coordinate vector of F with respect to G multiply it by P, you get the coordinate vector for V with respect to F. And you have the matrix Q. If you take the coordinate vector for V with respect to G, you get the coordinate vector for V with respect to F. Now, let's go back to linear transformations. Suppose we have a linear transformation T from a vector space V to itself. So we fix a basis, let's say F for V. So each vector in the basis, T of Fj, is some vector in V, so it's some linear combination Aij F sub I. I goes from 1 up to n. And we have the matrix for T with respect to the basis F. I write T with respect to F. This is the matrix Aij. This is the n by n matrix. And this has the property that if I take a vector V and take its coordinate vector with respect to F and multiply it by, let me call this matrix A, by A, I get the coordinates of T of V, the coordinate vector with respect to F. Or maybe I don't have to use A. Because this is this matrix T with respect to F. Or A, V with respect to F. So once you pick a basis for a vector space, you can write every linear transformation as a matrix. Of course, the matrix depends on the basis. So if we have a second matrix G, the matrix for T with respect to the basis G is given by, let's say, T of G sub j is summation Bij G sub I goes from 1 up to n. And the matrix for T with respect to G, I can call that the matrix B. And the matrix of T with respect to G times Vg is T of V G. Or this is the same as B times Vg. So this is maybe abstract notation that you have to get used to, but the emphasis is on the words have to get used to. This is how you do linear algebra. So you have one linear transformation, that's not changing. You can write it as a matrix A with respect to the basis F, and you can write it as a matrix B with respect to the basis G. So if you know that, say, the matrix B, how can you get the matrix A? What is the relationship between A and B? And the relationship comes from the change of basis matrices. So recall change of basis matrices. We have a matrix P applied to the vector, the coordinate vector of G. You get the coordinate vector of V with respect to F. The matrix Q applied to the coordinate vector of V with respect to F gives the coordinate vector of V with respect to G. So suppose we're given V in the vector space, and this is its coordinate vector with respect to F. So Q applied to the coordinate vector of V with respect to F is the coordinate vector of V with respect to G. Actually, let me do it the other way, so it's similar to what I just said a moment ago. So I have the coordinate vector of V with respect to G. And if I multiply that by the matrix P, I get the coordinate vector for V with respect to F. Now the matrix A has the property, this was the matrix A applied to the coordinate vector for V gives me the coordinate vector for T of V with respect to F. That is, if I have the coordinate vector for V and apply A, I get T of V, the coordinate vector with respect to F. So if I multiply this by A, I get the coordinate vector for T of V with respect to F. And if I multiply this by Q, I get the coordinate vector for T of V with respect to G. But B times the coordinate vector for V with respect to G gives me the coordinate vector for T of V with respect to G. So this matrix and this matrix, they operate the same way. And the matrix representation of linear transformation is unique. So therefore, B is equal to QAP, or if you like, because Q is P inverse, this is P inverse AP. So this is a rule for how you transform the matrix of a linear transformation when you change the basis. B is the matrix for T with respect to G. A is the matrix for T with respect to F. If I multiply this on the right by P and on the left by P inverse, I get G. This is sometimes called conjugation, when you multiply something on the left by an element and on the right by the inverse of the element. So this is sort of conjugation of a linear transformation. Right? Yeah. That's what it is. Okay. This is all linear algebra, beginning linear algebra. Because we're using matrices and coordinate vectors, it's very computational. And maybe I'll stop at this point because we're doing a lot. But I'll spend Wednesday's lecture talking exactly about this, how you use the change of basis matrix P and its inverse Q to have a formula for changing the matrix of a linear transformation. Okay. All right, well, that's a fair amount to digest. So hope that makes a good lunch, I guess. Looks like a nice day outside. Hope that everyone gets a chance to enjoy the day. Be back on Wednesday. Any questions before I stop? Okay. Take care all. See you Wednesday.